Okay, so this is lecture number 1. Okay, yesterday it was just knowing each one another. Okay, so we'll start today in just a minute. I do not know. Okay, Snigdha, are you joining using some other ID? Because I have to admit people and I do not know why do I need to admit people when all the invites have been already sent. Okay, so yeah. Okay, so this is lecture number 1 and the course is about phase lock loops. And we will see today where do we need phase lock loops and what is actually required to be done by the phase lock loops. Okay, so now what I can tell you about phase lock loops just to begin with is this is a block which generates some kind of periodic signal. Okay, so we have a PLL as a block and the output of this block particularly this is going to be a periodic signal. Okay, and I wrote it as periodic signal not as particular clock or sine wave or something because you can have periodicity for different kinds of signals together. Right, so you can have a square wave which has a period, a square wave, it can have a certain time period. You can have a sine wave which also has a certain time period, right? And by the way, you can also have a triangular wave or any other wave, let us say. So you can have a triangular wave which can also be periodic. Okay, so if I talk about periodicity, it is something about, let me just draw it to tell you what periodicity we are talking about. So we can have a square wave like this, for example. Okay, this is our square wave which has a certain period t, and when I say a certain period t is this. Okay. Similarly, we can also have a sine wave whose period is also t. Right, just assume this is a sine wave, and we can also have a triangular wave whose period is same as the square wave. So all these signals are periodic. By the way, it appears like sine and triangular wave are same, but they are actually different. So both square wave, sine wave, triangular wave, all these are periodic signals here. A PLL is a block which generates periodic signal. Most of the time it is going to generate either your square wave or sine wave. But if it generates triangular wave also, there is no problem with that. Okay. So it depends on the requirement. Now, this particular value which I am calling as t, this is called as time period of a signal. Okay, time period. And the question is, okay, so PLL is just a block which is generating this periodic signal, so what's so great about it? Okay, and the answer to that is, this particular time period is something which governs how fast we are doing things with our electronics, or how fast we are sending information from one point to the other, right? What kind of wireless transmission we are having. So this T is going to decide all that. So let us just look at a few applications one by one where your clock period will become important. So let me first pick up a wireless application where you need a PLL. Okay, so for example, people who know a little bit about the wireless transmission, they will know that what we do in case of wireless transmission, we actually have a baseband signal. A baseband signal means this is our actual information. I can say this is FPB by 2, let us say, in frequency domain. So this is our, you can say, an input signal X of F. I am just showing you in frequency domain. This is our signal, right? So what you do is you mix this signal here. You take this signal, mix it with a local oscillator, which is nothing but a clock. Okay, so your X signal comes here. You have your local oscillator sitting at certain frequency F0. See, when you have a clock, you will have a frequency. So I am calling that frequency of the clock as FLO. When you mix these two signals, what you are going to get at the output of your mixer has a signal which is centered around F of LO, and you will have your input signal which gets up converted with FPB by 2 and minus FP by 2. So FLO plus FP beta by 2 and FLO minus FP by 2. So this is how once you get this signal, you actually have then apply this signal through a power amplifier to the antenna, right? And this is how you transmit your signal in wireless medium. Okay, so now if you see here, when you are talking about cell phones maybe 10 or 15 years back, you might be using GSM. Okay, then some other time you move to GSM, or then 2G and 3G and so on, 4G, and now you are talking about 5G. Okay, so in all these cases what is changing is not okay, I have to keep on flipping here right now. So what changes here is, in your wireless case, your FLO is changing for different standards, okay, and surely your F bandwidth is also changing. So if I take it like for different wireless standards, 2G, 3G, 4G, and now 5G, and maybe you wait for another 5 years, you will have 6G, right? So every maybe a 5 to 10 years time, you have another wireless standard. And in that wireless standard, what we are doing is, we are doing two things. One, we are increasing our F bandwidth. Okay, so whatever information we are sending from one point to other, right, that information is available in this baseband signal. Okay, and how much information can be delivered, that is proportional to your bandwidth of the signal. So as we keep on going from one standard to the higher standard, your bandwidth is increasing, and at the same time what we are also doing is we are changing our LO frequency to higher frequencies. Okay, so you have to generate this LO frequency, local oscillator, the clock frequency, to be very precise, okay, such that you can convert the baseband signal to certain carrier's frequency and transmit. Now, to comment on the preciseness, let me tell you, let us say this is a GSM signal. So how transmission happens, let me just tell you, if there are multiple users, so you have a certain band around your 925 to 900 some meg. Just take an example, so it's not exactly in numbers. So 900 meg plus 900 meg plus some delta F. So this particular band is allotted for GSM applications. Okay, within this band, each of you at any given time of communication, each of you will have a certain bandwidth allocated to you guys. Okay, so this is the only bandwidth which is available for you to communicate, and this bandwidth is only, in case of GSM, is only 200 kilohertz. Okay, so you have your wireless receiver in your phone, and you are 2 or 3 people, or let us say more people are there, and each one of is able to talk. Just think about it. So this signal is coming at your receiver antenna, and you are getting this signal, and you will have surely matching network and so on with LNA and everything. You have to down convert this signal back to your, so you have to down convert this signal using the local oscillator back to your baseband signal, which is where your information is located. This is what I need to do. Now what happens is, multiple users are allocated different signal bands. Okay, and as I am telling you that you are having only 200 kilohertz of bandwidth, so whatever LO frequency I am generating, I have to make that LO frequency centered around the frequency band which is allocated to me. Okay, so it's like two different receivers. So let us call that as user A and user B. So and let us say both of them are roughly at the same place. Okay, so here this is user number A, okay, and this is user number B, and you are getting the same signal, or because the two users A and B are very close by, so they are seeing both this. So let us call this as user A and this one as B. They are both getting the same signals. Now user A has to generate frequency LO1 and user 2 has to generate frequency LO2. Then only those two people are going to get their respective signals. So I am just highlighting that. So let us say one signal, oh this color is really bad. So one signal is this is user B signal. Okay, and then you have user A signal, which is this one. So user A should get only this, and user B should get the signal corresponding to user B signal. Right? Now you just think about it. If the way I have shown you, the bandwidth of the signal is only 200 kilohertz, then difference between LO and LO2 frequency, LO1 and LO2 frequency is very small. Okay, and you have to generate this LO1 and LO2 frequency on your cell phone, right? And it is not always the case that once you have bought your cell phone, your LO1 frequency will always remain fixed throughout the life of the cell phone, or you change your cell phone, or you change your operator. It's not like that. Sometime you may use LO1 frequency for channel located here. You may use LO2, you may use LO9, and so on. Whatever is given in that standard. So your clock generator has to keep on changing your frequency here. Okay, so here I can say this LO frequency is nothing but some 900 megahertz plus some integer times 200 kilohertz. Okay, at the same time you can, at the same time and same place, you cannot have normally same LO frequency for the two users. At the same place you can't have, at different places you can have. Okay, so what your PLL chip, which is PLL IC, which is there in your cell phone, it is generating the LO frequency as required, as accurately as required. Okay, so that is the job of the clock generator in wireless application. Okay, any question with this? Yes, guys? Okay, so if you look at this wireless application and you see that you require some exact frequency, okay, and by the way, when first I just showed you as a sine wave, and then I told you, okay, you have a LO frequency and this is how you are going to mix it. Well, I am going at a very top level. Right now we are not going into details, just to show you where it is used. So by the way, when you have a sine wave as a clock which is shown here, the frequency domain spectrum for a sine wave is just a single frequency here. So if the time period is t here, this frequency is going to be 1 over t. So this is what you can say. In time domain, this is x of t. In frequency domain, this is going to be x of f. Okay, so when we mix in time domain, this is, well, you can use all the maths here to tell you that a certain LO frequency, which is the spectrum of this clock, is going to be just one single frequency, and then you will, when you mix it, you get such kind of modulation. Okay, and if you have even a slight curiosity, how do you get it? So let me just tell you, if your x of t is a signal which is let us say a or am time sine of omega mt, right? And your LO signal, so I will write this as let me just say x of LO times t. This is going to be, let me write it, cosine of omega LO t. And when you mix these two signals, let's make it as u. So when you mix this u of t with x LO of t, what you are going to get is, you can write it together. What's happening here? Just a minute, these things are, yeah. So you have am times sine of omega mt times cosine of omega LO t, right? You apply a little bit of maths and you are going to find this is nothing but am by 2 into 2 sine a cos b, which is going to be sine of omega LO plus omega m times t plus sine of omega LO minus omega m of t. Okay, so what you see here is, when you mix the signal, when you up convert it in your RF chain, radio RF transmitter, you have omega LO plus omega m, omega LO minus omega m. This is what exactly I did here. I have this LO frequency here, I am having f bandwidth, so I get omega LO plus f bandwidth, omega LO minus f bandwidth. Okay, f LO minus f bandwidth. So you, the bottom line is that you need a very precise generation of clock on your cell phone chip for any wireless transmission, and that you should be able to actually vary that frequency as and when desired. Okay, so your clock generator which is sitting on your cell phone is doing all the hard work. Okay. Next thing is, if you look at the communication which is happening right now, is like I am connected with my laptop to an Ethernet connection, and then Ethernet goes to the network place wherever you have the network switches. So what you have is, you have a location A, multiple places, you can just check that. I am just calling this as location number 1, and you have another location number 2, and just think that we are actually communicating with wire which is given here. There is a fixed wire which is connected between the two locations, and these two locations are communicating with each other. and you very well know this is some kind of Ethernet communication which can happen between two locations. Okay, and similarly it is not only between two different locations with an Ethernet connection. You can have your processor, which this processor can be the processor in your phone or the processor in your laptop or in your workstation, and then you have a memory. Okay, by the way, processor is just doing the computation. All the data which is used by the processor is coming from the memory. So you have actually multiple parallel lanes which are coming, which are connecting the processor and the memory, and this is not a wireless communication. There is a hard wire, there is a copper wire which connects the two, or maybe some other wire, and they are also communicating at certain rate. Okay, so now why is the clock important? The clock is important here because if you look at it, the communication which is happening happens at a certain data rate. Now all you guys are must be quite techy, so you must have seen that, okay, what is this DDR4 or DDR3 or graphics, a special DDR RAM for your graphics, right? So here if you see, the data rate will actually keep on increasing with every new standard. And what is the data rate? The data rate is what rate you are communicating between the processor and the memory. Okay, and this data rate, it can range from Mbps to multi-gigabits per second. Okay, Ethernet, if you are looking, you may be looking for a 10 gigabit per second Ethernet or something. Okay, now the question is, when we say this is 10 gigabit per second or certain megabit per second, what does it mean? So it means, if I just write the definition of the data rate, it is number of bits transferred, right, divided by total time taken. So you can just write it as an expression, how many bits are transferred per second, and we are saying that we are transferring 10 gigabit per second in our Ethernet connection. Okay, so who is making sure that in 1 second you are able to send 10 gigabits? Okay, so there should be some measurement. So how is it done? You generate, let us say you generate a clock, which is, here I am showing you a square wave clock, by the way. So I generate a clock which is 10 gigahertz. So at 10 gigahertz clock, which implies that my period of the clock is going to be 1 by 10 into 10 power 9, which is 100 picosecond. So this period is 100 picosecond. And how do I make sure I do a communication at 10 Gbps? At every rising edge of the clock which I have, I transmit one bit. Now that bit can be 1 or that bit can be 0. Okay, and it is a random, we do not know what that bit is going to be. You can have multiple zeros, multiple ones, or so on. But important part here is that at every rising edge of the clock, I will transmit a bit, whether it is 1 or it is 0. That will decide by what information I have. So this is how we keep in account how much data we have sent from one location to the other location. Okay, and if we want to increase the data rate, we will increase the data rate from 10 Gbps to maybe 50 Gbps or 100 Gbps. The days are not far when you will have your 400 gigabit Ethernet at your home, right? So this is where you need to have a clock. Okay, similarly between processor and memory, you need to have a clock. Now in this kind of communication, this is normally called as wireline communication, by the way. The previous one was wireless and this is wireline. Why is it wireline? Because you are communicating across a wire. Okay, so here this particular link is fixed, you are just communicating. Now you would think about it, how difficult it is to just have a communication across a wire. It is not that difficult at all. So let me correct you here. When we are doing this wireline communication, right, first thing is you need to generate a clock with the exact period of 100 picosecond. And if, let us say, at some point of time you do not get this clock, because this is generated by circuit, right, you do not get exactly at 100 picosecond interval, you may get something here, right, then it may become a problem. So your clock should ideally come always at a fixed intervals. Okay, and in general for this particular kind of communication, you make sure that if you transmit certain number of bits from one side to the other side, right, so when you receive the bits on the other side, you should not have more than 1 bit error in 1 trillion bit errors. Okay, so there is something, why did it just move? So there is something which is called as bit error rate. Okay, and this is this measures that how many bits when you receive at the other end of the transmitter, how many bits are in error. So what we need for above communication is bit error rate less than 10 power minus 12, 1 error in 1 trillion. Okay, so here if your clock deviates, it creates a problem, so you have to have some kind of performance requirement from the clock. Okay, so this is where another you see you get the clock. Okay, now another application, if you look at it, is well, everyone knows there is something called as analog to digital converter. So let me tell you how in analog to digital converter your clock plays a pretty important role. Okay, so just think, see that if you are having an analog signal like this, okay, and you want to sample this analog signal and you are listening to some really quality music, okay, maybe using your Bose headphones or some other specific headphones, and you have an analog signal. That analog signal should be sampled. So if it needs to be sampled, well, you will sample at a fixed rate, and for that you need a clock. So I need a clock to sample the signal, so I will use that. Now how am I going to sample? At every rising edge of the clock, I am going to sample the value. So here I sample this value, and then I get the next rising edge. This is another sample value I choose, and then I choose another sample value, and so on. So these are all the sample values which you get from the analog signal, and later you will convert to digital and so on. Okay, now important part here is, if your rising edge does not come at the correct point, first rising edge comes here, let us say this is time period t, second rising edge comes at a different time. It does not come at time t, it comes at t plus some delta t. Okay, there is some deviation here. Then your sampling point is going to move. Okay, and then maybe other rising edge comes before, right, then your sampling point moves. So all these change in the sampling points because of a bad clock or a clock which is not able to generate the clock with a fixed clock period, you will have a performance degradation from your analog when you convert from analog to digital signal, or even when you convert from digital to analog signal, you will have similar performance degradation. So having nowadays, when you have like you want to digitize a large bandwidth of the signal, large signal bandwidth, you need really high frequency clock and very less deviation in the clock time. Okay, so this is something which you need in analog to digital converter. Okay, any questions with these three applications? What kind of clock is required in these three applications? Yes, both will have the clock. No, but the whole thing is that your clock may not be same for both. Or when you say that both are using the same clock, right? How do you ensure that both of these things use the same clock? So that's a different thing. So we can, in case of wireline communication, we can change the data rate if we are changing the frequency. That is true. Your previous question was, if the clock gets delayed from processor to memory or so on, it will not be any problem. I did not get that question. Can you clear that? So delayed by same amount, or both of the data rates changes by the same amount? No, the delay is not the data rate. Okay, so let me just make it clear. So let us say if you are transmitting from processor to memory at every rising edge, okay, you are sending a data to the from processor to memory. After you have done computation, you are sending data back to the memory, right? Now if I delay the clock, what it means is that I am changing the rising edge of the clock, okay, but I am not changing the period. Delay doesn't change the period. It is like a time shift. In place of, so it's like this, see, whether I am sending data at 10 Gbps, whether I am doing it now or I am doing it 1 hour later, my data rate does not change if I am doing it at 10 Gbps both the time, right? So delay is different from the time period. Okay, and yeah, any other question? So there are roughly some 40 students in the class. At least certain number of people can ask questions, right? Okay, so what we have seen is that in wireline, wireless communication and in ADCs you have such kind of clock requirements. Okay, the other places where you will need clock is like, well, we have talked about more of analog things. In digital cases also you need a clock. For example, let us say you are getting a clock and you are driving some load. So you have a buffer and then you are driving some combinational logic here using the buffer, and you may have certain sequential logic in digital circuits, right? So when you do all such kind of things, multiple circuits, right, you have, and you are feeding a clock here. Okay, now depending on how much, whenever you connect something to the buffer, this is a circuit block, right, you are going to add parasitic capacitance at this node. Okay, so what happens is the actual clock, so this is my ideal clock at the input of the buffer, okay, and the clock which reaches at this combinational logic is no more, this is no more actually such a nice signal. It may become like this. depending on the load, this signal may become like this. Now, the signal is periodic. There is nothing that the signal is not periodic, but if you look at the signal, it is no more like a square wave signal or a CMOS signal which you can use in the digital circuits anymore. Okay, so this is where your clock may come in the picture, where you may clean, so you may get such kind of signal, right? But what you are going to do, you may clean this up and then you will bring it back to the same square wave signal. This job is also done by clock generators, okay, in case of digital circuits. The other place where you will see clock is some kind of tunable filters. Okay, so this is a little bit, if you have not done some kind of switch capture circuit, then you may not know, but just for completion's sake, I will tell you here. So what you can do is, so let us say you are using a MOSFET and a capacitor like this. Okay, this is just an example. You have here V in and you have V out. Okay, and this particular switch is clocked. Okay, so when you have this switch clock, it's like the signal. This particular switch is on and off with a certain time period. Okay, so what you are going to find is that depending on what is the time period of this clock, your V in, V out by V in is going to have a certain bandwidth. Okay, we will, I think in your analog course or some higher level course, you will learn about the switch capture circuit, where depending on the clock frequency at which you are actually trigger switch you are using to switch the MOSFET on and off, on or off, you can change the filter bandwidth. Okay, there you require proper clock period. Okay, because your filter bandwidth becomes a function of the period. There is no video? No, are you able to see the screen or no? Okay. Okay, let me just redo that. So, since when the presentation is stopped? Huh? Okay, since I started the filter. Okay. Okay. Now you can see. Okay. So what I was talking about was a tunable filter, and in case of tunable filters, you use a clock MOSFET to vary the filter bandwidth. Okay, and the filter bandwidth is actually a function of the time period at which you are clocking the switch. So there also you need some kind of precise filter. Why do you use such kind of filters? See, if I want to have a simple low pass filter, I may use R and C. Okay, and you fix your R and fix your C, so your filter bandwidth will be fixed. But what happens is, when we want to vary the filter bandwidth, right? The only way to vary the filter bandwidth is you vary your resistor or you vary your capacitor or so on. Now varying resistor and capacitor is quite problematic. Okay, so what one can do is, in place of using a fixed resistor, you can use a MOSFET and you can clock that MOSFET. And when you clock that MOSFET, you actually you will find out that when you clock a MOSFET, you change the effective resistance, and when you change the effective resistance, you change the effective bandwidth. So depending on the time period of the clock which you are using for this filter, depending on time and off time, so this is like on time and the rest is half off time. I am showing you most of the time a 50% duty cycle. Depending on this, you can actually change the filter bandwidth. So this is where you also need a clock. Okay, a precise clocking. Any variation in the clock is going to change, is going to alter your filter bandwidth, which may or may not be desirable. Okay, So similarly, you have if you see the applications, right? Any of the higher level course which you are going to do, well, you will not be able to just neglect the clock, right? So just think about it when you are thinking that okay, once I am going to have 5G, I will get a better bandwidth, right? So if you are getting a better bandwidth, someone there in the company or in research lab is giving you a better clock at a higher frequency. And because you are having a large signal, so in your cell phone there will be someone who has designed the clock which communicates, which helps you your cell phone to communicate between a processor and memory with a higher data rate, or so on. Okay, and also when you look for when you go and buy any of this electronic gadget, right? You actually look for okay, what is the clock frequency, what is this DDR, and so on. So a clock cannot be missed in any of these applications. Okay, the basic architecture of all the clock generators is the same. It is just what is more important, or what is more important performance metric for the clock generator in a given application that will drive you to design a particular clock generator. Okay, any question with this? Okay, so now I hope the application of this phase lock loop is at least at a very top level is visible to you. Now we will see that okay, I need a clock. So what's so important? I wear a wristwatch, whether it's a Fitbit or something that also has a clock, and whether there is a timepiece which always ring in the morning and I never wake up. Right, that is also a clock. So what is this? That clock is also working, this clock is also working. So what's the difference between the two? Okay, so first thing is the clock which you guys, not the electronic clock, let me put it that way, but the clock which you have been using in your home maybe from old days, is that clock works on the piezoelectric effect from a quartz, or for a quartz crystal. Okay, this is the natural clock which you have seen, or natural in the sense that you have a quartz crystal. It works on piezoelectric property. Okay, and it creates a certain depending on how you bias it and you provide the energy required, you have a certain number of vibrations for this crystal per second, and it is very precise depending on how you manufacture it. Okay, so the clock which you have been using for such a long time, which is not that electronic digital clock, is working on the mechanical property of a quartz crystal. Okay, and this particular quartz crystal generates a very clean clock. Okay, I am using qualitative word clean, which is like a quartz crystal is going to produce a very clean sine wave whose period is almost fixed. Okay, it will generate a very clean sine wave, not do not judge the cleanliness by the drawing which I draw here, but just take my word for that. Okay, so a quartz crystal produces a very clean sine wave. Now we are electrical engineers, we do not worry about that much of the mechanical property, but that is where the clock comes from. So the thing is, this particular quartz crystal will generate a clock. Normally the frequency of the crystal is low. Okay, the frequency of the clock is not that high. It may be running in kilohertz and megahertz, maybe some best of the crystals may be running at maybe hundreds of megahertz. Okay, so frequency is quite low, right? We are talking about 10 gigabits per second, and then having a quartz crystal which works at 10 gigahertz will be either not possible, not feasible, or it is too costly, right? You do not want to buy your cell phone like for 10 lakhs, right? So surely it's not possible that way. Okay, Now the other thing is, once you manufacture a quartz crystal, the frequency is more or less fixed. So you cannot tune the frequency of the quartz crystal that much. Okay, so let me write it. Tunability is T is less. Okay, or let me just say not tunable. So you manufacture a quartz crystal, you get a, let us say 19 megahertz of the frequency, you will get 19 megahertz. You cannot go and do anything to that crystal to change the output frequency. You cannot increase the frequency for sure. Okay. Good part is, you can say variation is in clock period. Variation in clock period is least. Whichever clock you are going to have, the variation in the crystal clock frequency, a well designed crystal clock frequency is going to be very less. Okay. So if you want to look at this crystal which is used in your timepiece or so on, or your wristwatch, is that good property is variation in the clock frequency is least, bad property is frequency is very low and it is not tunable. So this is bad and the other one is good. So as always, we will like to take the good part and try to somehow deal with the bad part, or do something to overcome the bad part. Okay. So what we see is there is an electrical equivalent of the crystal. And what is that electrical equivalent of the crystal? Electrical equivalent of the crystal is an inductor. Okay. And you have a capacitor also associated with it. Okay. So inductor is a real system. Inductor is going to come with a resistor, and then you have a capacitor connected with it, and then you may have another parasitic capacitors connected on the side. This is just an equivalent of a crystal, nothing more. Okay. So you will see that if you remember your 12th class maths a little bit, right? You might have studied about spring mass and all those things, isn't it? It's like a second order system which is oscillatory in nature. And then you would have seen the inductor and capacitor equivalent of this. Similarly, you can just think about it. Okay. And the frequency of oscillation, or the clock period, right? This frequency of oscillation is a property of the inductor and capacitor which are present in the system. Okay. And you can work it out. You will see that this frequency of oscillation is inversely proportional. So omega oscillation is inversely proportional to ln C. Okay. So this means that if I want to increase the frequency of oscillation, I have to reduce the inductor and capacitor value. Well, crystal has, because this is electrical equivalent of a mechanical system, inductor value we cannot change, capacitor value we cannot change. Okay, so we cannot change that, but what we can do is we can have our own inductor and say, okay, I will have my own inductor and I will make it oscillate. Okay, at the frequency at which I want. So let me just draw it in a different manner, or just do it like this. I have an inductor and a capacitor connected like this. Okay, and what I am going to do, I am going to, this is C and L, I charge this capacitor to Vc at t equals 0. Let us say capacitor voltage Vc of 0 is some V voltage, V0. Right, and just leave the system as such. What you are going to find is that your V out is going to be a sine wave. You can work out this maths. Okay, it's going to be a sine wave where omega naught is equal to, or the frequency of the sine wave will be 1 over L. Okay, if we use our own inductor and capacitor, then there is no limit. The only limit is that we can manufacture how low inductor and how low capacitor. Okay, and we can get any frequency we want. So you can think that okay, we solve the problem. But so if we want to change the frequency, we can vary these component values. No, but the problem begins like this. First, this inductor comes with a resistor. Any inductor you design, it is made up of metal, it will have some resistor. So if it is made up of some resistor, what is going to happen is your frequency, your output clock waveform will just die down. Okay, if you just charge this capacitor once and just leave it like that. So that will not work. Other thing is, this capacitor and inductor, these two things are actually going to vary, and because they vary, you are going to have because they vary, you need to fix the frequency. How are you going to fix the frequency and so on? Well, that is the part of this course. Okay. So you have a naturally clock frequency which is available. You cannot get all frequencies which you want. So you come up with some kind of electrical equivalent that okay, I will have some block which can generate the frequency. You tried that. Ideally it works like LNC, but practically it does not. So you have to overcome those challenges. The only good part here is that you are getting whatever frequency you need if you can change your LNC. But either the frequency, the system stops oscillating, or because the component values vary, and if the component values vary, then you are going to have a problem with the output frequency. Okay, and all these problems will be sorted out by your phase lock loops. Okay, so let me stop here. If you have any question, let me know.